right, let's get the party started. Hey, hello everyone. Hope you are all well, all safe regarding everything that's going on. Let's actually jump into it. This is a notebook. Yeah, so this was what we were dealing with yesterday. Okay, so just before we get started, I sent out an email through Jupyter Grades just a few minutes ago, like 5 minutes ago or so. Please make sure that you got that email. So the past 2 days, I've been sending out messages from multiple sources because I don't know what sources you guys are checking, but I'm going to consolidate communications, and I'll be sending out mass emails mostly or only through Jupyter Grades moving forward. So if you have not received that email, that might be an issue because you're potentially missing important communications from me. So just make sure that you got a Jupyter Grades email literally about 5 minutes ago. So it's about 1:25 on today. If you didn't receive that communication, then chances are in the future you're going to be missing communication from me. So make sure that you have that. In terms of what we've already covered, I'm not going to do as much of a recap with the syllabus and all that good stuff. At this point, I assume that everyone is kind of okay with that stuff. Go back and watch lecture 0 if you have not already. Make sure you fill out the questionnaire and all that good stuff. And we're still a few people shy. I think there are still about 3 people missing, but most of the class is here. So we will begin. As always, I'm going to, some more people trying to get in. As always, we will turn off the video and get started with the lesson. So just a brief recap on what we did yesterday before we get into the new material. So yesterday we reviewed what a differential equation was, what an ODE is, what a PDE is. We also defined what the order of an ODE is, and this is just the number of the highest derivatives. So if you see a second derivative is the highest derivative that appears, then we say the ODE has order 2, and so on and so forth. Right now we're doing with chapter 1 where we're looking at first order ODEs. These are differential equations which have the first derivative is the highest derivative that appear. And of course, we are doing ordinary differential equations. We're thinking of single variable functions where there is a single independent variable, and we have equations that involve the derivatives of the function. We looked at a very simple kind of differential equation, dy dx equals y. We figured out the solution by inspection as well as with a more analytic method, as we'll call it. Analytic just means you can solve it by hand. What we used here was separation of variables. That is also something that we looked at in general yesterday. So that is one of the first methods. We did a bunch of examples solving differential equations via separation of variables. And remember, that just means you can write the differential equation in this form. So it's purely, you can write it as a function of y times dy equals to some function of x times dx. So it means you have to separate the variables, usually through multiplication and division, because if you add things to both sides, they'll be separated from the dy and dx, and that's no bueno. So once you can actually do that, you integrate both sides and you can get the solution. Of course, this is assuming that your integral will work out, you can integrate it. In the event that you cannot integrate it, which in this course, we're not going to see this scenario, right? Everything I will ask you to do, you will be able to integrate it by hand. But in the event, in the quote unquote real world, that you cannot actually do the integral, you would just approximate the integral using some numerical methods. And those you learned about back in Calc 2. But in theory, you can always for most functions, you can integrate them. If you can't integrate them with some formula or some sophisticated method, you can just brute force, have a computer create Riemann sums or some other approximation technique to actually compute an integral. So that is the separable method. I will be teaching you many methods. The separable method is one of the easiest ones to apply, and so it's one of the ones you're going to look at first. Now, once I've taught you a bunch more methods, I'm going to tell you about, I'm going to give you suggestions as to when you might think to use what method, what do you look for, and kind of what order in which you want to think about them. So yeah, we covered that. We also looked at direction fields. This is another method for solving ODEs graphically. Basically, you plot the slopes. You plot a bunch of slope vectors in a space, and then you follow the curves. You have the curves follow that slope. And you can have a variety of graphs that will fulfill that need. And you can just pick the graph that passes through the coordinate that you want, and you can have a computer or something else interpolate what a function that can approximate that graph. So that was another method. This is the method of direction fields. Now, it's not a method we're going to use often, but it is a fundamental method that is out there. So I just thought I would show you guys about that. And this was mentioned in chapter 1 as well. And that's kind of where we left off. One last thing in chapter 1 is population models. So they wanted to show you an instance of when first order derivatives can be used to model some real life situations. And population growth is one such situation. Now, there are many models for population. We're going to look at one of the most naive ones. It's called the Malthus model, which is, the Malthus model is a very specific case for something called the harvesting model. So we're going to look at the harvesting model of a differential, of a quantity that's growing exponentially. Okay, so let's talk about that. We all know about linear growth. Linear growth is what you have when you have a quantity growing by some absolute value or decreasing by some absolute value per unit time. So you can say, okay, I have a quantity, I know there are 10 units of that quantity right now, but it's increasing by 2 units every minute or whatever, right? So it's always increasing by 2. So I know 1 minute later, I'm going to add 2 to it. It's going to become 12. After another minute pass, I'm going to add another 2 to it. It will become 14, and so on and so forth. This causes linear growth. If you were to plot this on a graph, you will have the plot of a straight line. Now, there's another kind of growth, which is you are growing by a fixed percentage per unit time. So you can say, oh, this thing is growing by 2 percentage points per unit time. Every minute it grows by 2 percentage points. So at the first minute, it's going to grow, if I start out with 10 and it's growing by 2% per minute, then after 1 minute, it's going to grow by 0.2. And then after another minute, it's going to grow by whatever 2% of 10.2 is. And so what you'll realize is that it grows by more and more over time. So it grows based on a proportion of what the current value is. And it turns out that populations grow in this way. So the more people you have, the more babies you will have, and the population is going to grow faster. So a population of 10 people is going to grow a lot slower than a population of 1,000 people, because 1,000 people are going to have way more babies, and eventually those babies will have babies. So you're not growing by a fixed amount per unit time, you're growing by a fixed percentage per unit time. So you can talk about the population of the percentage of the population that is reproducing, and you can make a model based on that. Essentially what this means is that if I let P of T equals the size of the population, at time T, the harvesting model assumes that the rate of growth of P prime, is going to be some fixed proportion of the original population. So R is the percentage growth. It's also called the relative growth rate. Maybe I should write out the word relative. It's also called the growth constant. P in this case, this is called the rate of growth. Don't mix up rate of growth with growth constant or relative growth rate. And that's P prime, and P is the current size of the population. So this is making the assumption that based on the current size of the population, it's growing by a certain proportion, which we call R. And then on top of that, the harvesting model includes this plus H. So this is almost like a linear portion of the growth. This is a fixed amount we are growing or decreasing by. Okay. Now, once you have that, this is called the harvesting model of a population. Okay. So if this differential equation describes the rate of growth of a population, we say it's called a harvesting model. Now, if H equals 0, we get what's called the Malthus model. If H equals 0, meaning I'm only thinking of the population growing by itself, with influence, this is called the Malthus model. Now, these are things that you will see in a biology class that will typically cover population growth, right? And there are many models. There are logistical models that account for carrying capacities and all of that stuff, but this is one of the most naive ones. So how would you know you'd have to use the harvesting model? So this is, for example, if you have a population that is growing by, say, 2% per year or whatever, for example. But at the same time, you know that on average, 100 people per year move into this population, right? So it doesn't have to do with the growth of the population itself, but there is some external factor that's causing regular growth or decreasing to the population. That is what the H is. So if you wanted to model, so example, if you wanted to say a population grows by 2% per year and 100 individuals, let's make this interesting. Let's say they leave the population. Yeah, H can be a death rate. Then you just think of it as negative. They leave the population. You can think of leaving as through death or them just moving out or something like that. We're not going to get too much in specifics. What's important to us is this differential equation and how to solve it. But this is an application, so leave the population per year. Find an equation that models the size of the population P of t at year t. Assume the population starts with 1,000 people. Okay, so here is an example of a situation, right? So a very naive way to model this situation would be a harvesting model. I have a population and I know what its percentage growth rate is. I know that 100 individuals leave the population per year. So the population is decreasing by a fixed amount of 100 individuals per year. And I want us to find an equation that models this population, assuming that we start with 1,000 people in this population. So we have 1,000 people, 2% of them are having babies every year, and then 100 people move out of the population every year, okay? If I wanted to know, okay, if I knew a point where there were 1,000 individuals, how many individuals will there be in that population 5 years after the fact, right? I want an equation that's going to give me that information. So what we can do here, this is something that's we're going to look at later. What we can do here is start with a differential equations model. The model is going to be, well, the rate of change is going to be 2%, 0.02, times the original population minus 100, right? So that's the harvesting constant. You will notice, note, this is a first order. It's also separable, ODE, which means if I want to find the P of T that models the population, it just comes down to solving a first order separable ODE. All right, so we covered a lot of that yesterday. So at this point, maybe one of you guys can tell me how to actually finish this up. Also note, we do know the initial condition. What's the initial condition here? Right. So remember, the initial condition is an equation that tells you about the value of the function at some point in time. I know if we start, we can think of that as time 0. We start with 1,000 individuals in this population. Okay. So now, all right, how do we go about solving this? So if I have p prime equals 0.02 p minus 100, how do I solve that? What's the first thing you want to do? What do we do? Separate the variables. Yes, I did mention it's separable. I want to know, how do I get this done? Tell me, what would you do? How would you separate it? Okay, so we have a suggestion here to actually subtract p prime, move it to the right, and then move the 100 to the other side. No. Now, why is that? So let's say we move this over there, right? And we have minus 100. Why is that not good enough for separating the variables? Right, p prime is equal to dp dt. So you have not separated the variables. There is a t on the left side, right? So you have not separated the p's and the t's by doing that. Okay, so how do we get it done? How do we separate the variables? And yes, you can remember that this is dp over dt is equal to 0.02 p minus 100. Okay, so you rewrite the p prime, move the dt to the other side. Okay, so this is going to mean that dp is equal to 0.02 p minus 100 times dt. Then right, you divide by that whole thing. So here we have dp over that. Okay, So now to recap on something that I mentioned yesterday, remember, addition and subtraction is almost never what you want to do in a separable situation. Separable means you can write it as a function of the dependent variable times d, so a function of y times dy equals a function of x times dx. Adding something to both sides is almost never what you want to do. You want to move things across the equal sign via multiplication and division. You need them to be attached by multiplication to the differentials. Okay, so when you think separable, stop thinking adding and subtracting. You should be thinking multiplying and dividing. Okay, you need to write it as something times the dp and something times the dt. Okay, all right. Okay, so these are things that you should make a note to yourself about. So write in your notebook if this was a mistake you made or this is something that you thought. Put an asterisk. Make a note to self. This was a mistake I made. This is why it's wrong, blah, blah, blah. Okay, so these are things you should be making a note to yourself about. Okay, so at this point, the variables are separated. We can integrate both sides. All right, what is the integral of the left side? Integral of left side, anybody? If you don't want to type it, you can say what it is. I know typing sometimes takes forever. Now this one's not too bad, but eventually the integration is going to get really hard. So I do want to make sure that we know the fundamentals, the basic integrals, because eventually by maybe the end of this class or maybe in the beginning of next class, we're going to have more sophisticated techniques like integration by parts and partial fractions and all that stuff. So, all right. So technically you need a substitution here. You are going to have ln of 0.02p minus 100, but you need to remember to divide by that 0.02. Common thing to forget. If you forgot this, make a note to yourself. Technically, what you wanted to do was a substitution. Set u equals 0.02p minus 100, right? You don't have a single variable. You don't have 1 over a single variable times, you don't have 1 over p times dp. You have 1 over some expression. However, the derivative of that expression is a constant. So you say u equals the denominator, your du is going to be 0.02. You're going to have to divide by 0.02. That's 2 over 100. You're going to flip that to be, that's 1 over 50, which you're going to flip it and you're going to get 50. So this is 50 ln 0.02p minus 100. On this side, that's t plus c. Do not forget the plus c. Commonly forgotten. Do not forget. Never forget. Okay. Now, so we have this. All right. Now, this is the implicit solution. Find me an explicit one. How do I get to the big P? Take the exponential of both sides. What would happen here? Now, there's a potential for error in doing this, even though technically this is okay. I would guess about a quarter of students are going to make a very silly error if they exponentiate both sides at this point. Maybe some of you can see what that error is. Maybe some of you would even make that error. What would happen here if I exponentiate both sides?
Should we get rid of the 50 first? To the right?
Right, you would move the 50 first. A lot of students, when they exponentiate here, they just use the e and cancel the ln and they leave the 50 alone. That is incorrect. That is an algebra error that's going to get you in trouble. So what I would do, it's not that it's wrong, but you'd have to realize that you'd have an e to the 50th power times this guy left over. Most students will forget the e to the 50th power. To prevent forgetting the e to the 50th power, what I would do is first move the 50. So this is t over 50. Now, of course, c over 50 is just another constant. Leave it as plus c. Then I would exponentiate both sides. Now the e and the ln cancels on this side, so I have 0.02 p minus 100. What does the left side become? The right side. What does the right side become? Right, it's a constant times e to the t over 50. Common error here. Like, I've been teaching a long time. I can tell you what the error students are going to make is to write this as e to the t over 50 plus c. That would be incorrect. That is not correct. It's the c plus c will multiply by that. I explained why yesterday. I also explained why the day before, so I'm not going to go over that. So that's going to be it. And at this point, it's relatively simple algebra to solve for the p. I would just add 100 to both sides. And then divide both sides by 0.02. And I think that can simplify. Is that going to be a half? Okay. So now, is that our final solution? This here is going to be 2 over 100. Yeah, it's going to be. Okay, checking to see if you guys are falling asleep. But are we done here? You need to solve for C, right? So we have an initial condition. We know that P of 0 equals 1,000. This means when I plug in T equals 0, then my P is equal to 1,000. This is, of course, going to tell you that your C is minus 4,000. And so I would be able to say that my P is equal to minus 4,000 e to the t over 50 plus 5,000. Oh, why didn't we do? I did. So if I took c e to the t over 50 and I divided this by 0.02, then this here is just another constant. So it's still just some c. Right? Anything that involves an arbitrary constant, I just rewrite it as another arbitrary constant. There's no need to, like, I don't want to have to deal with c divided by 0.02. Just dealing with a c is okay. Okay. Now, from this, you can have all sorts of things occurring. For example, here's something that we can know. Question. If I were to ask you, what do you think is going to happen to this population? What would you tell me? Let's see if we can interpret these numbers here. Right. So ultimately, based on this random example that I made with made up numbers, this is the equation that would describe the population. Notice that it's exponential. Populations usually grow exponentially, right? Of course, it's going to be an exponential that's tempered. You mess with the power a little bit, you mess with the constant multiplier a little bit, and you might add or subtract the constant, things of that sort. But overall, the basic element of a population when it comes to growth, it's going to be exponential because the more people there are, the more babies there are. But what would you say is going to happen to this population? It's eventually going to die out, right? Like, or not even die, but eventually the amount of people that are moving out, it's going to create a situation where eventually there's going to be no one left in this population. Notice that here the exponential is going to keep getting bigger and it's multiplied by a negative number, which means that eventually this thing is going to go off to negative infinity. Now, of course, you cannot have a population hitting negative infinity, but eventually that's going to hit negative 5,000, right? When t equals 0, it's not currently negative 5,000, but eventually t is going to hit a value where this is going to exceed negative 5,000. And at that point, you will not have a population. Okay, so in this situation, you have a population where the way that it's not growing fast enough to sustain the population, right? So this gives us some predictive power. So there's all sorts of models and populations here. And when we make predictions about the future, we're making it in terms of some model. Now, the reality of the model can vary. In this case, we have a model that says, oh, a population can go off to negative infinity. We know that this isn't real. And this is why we can we have refined models of population, like logistic models and et cetera, where they don't do things like go off to infinity. This is a very naive model. It's called the Malthus model or the harvesting model. But it is useful in some contexts. There are times when it's a very naive way to look at a population. Then we can make predictions. Oh, this population is going to grow out of control, or this population is going to eventually die out. We need to have incentives to have people moved in, right? So when you see like states, there are a lot of US states that they actually offer money to people to move there. It's because of things like this. They're running these models that is talking about their population, and they realize, hey, our population, yes, like Alaska, right? They're like, hey, with the amount of growth that we're having and the amount of people moving out and in, our population is going to decrease after a while. We're not going to get as many Senate votes and whatever. So they're like, okay, we need to increase the population artificially somehow, right? Models like this, well, not exactly like this. This is a very naive model, as I told you. Models like this is very important when it comes to doing that kind of prediction. And yeah, when it comes to population, differential equations are going to be there in some way, shape, or form, because that's how you start. You start by figuring out, how is our population growing? Is it increasing? Is it decreasing? What is a function that would describe this population? That equation is going to be a differential equation. Then you're going to apply some method to solve that differential equation. And by doing that, you will predict what is going to happen to the population in the long run if all these conditions remain the same. And then you can decide, oh, we want to artificially change this situation somehow. And that's when you do something like, hey, let's offer people $2,000 a year to move into our state, right? So this is an example of where we can see differential equations come into play in terms of population control or measuring populations or predicting what's going to happen to a population, right? Very naive example. It is what chapter 1 sort of ends with, just a model. We will be doing more applications as well, but this is just a very naive one that we can do from the start. Another thing about this model is that it can be used in another situation. And you'll see problems like this in your homework, I believe. another place the harvesting model is used is in finance. Specifically, when funds are compounded continuously. Now, compounded continuously is not something that happens in reality, right? This means you're compounding an infinite number of times per year, right? You're applying compound interest an infinite number of times per year. Now, of course, in reality, that cannot happen. However, it is one of those things that we use to model like the worst case scenario. You know what I mean? Like if we have a debt and it's growing by a certain percentage and our creditor is compounding it an infinite number of times per year, that's the worst possible situation. Like how fast is our debt going to grow? What is the worst case scenario? The compounding continuously idea covers that scenario. It can't really happen in reality. However, that is a limit of what can happen in reality. So if we can control that scenario, we'll know that we'll be able to control any other finite scenario, right? So this is when you're applying compound interest on a continual basis. So if P of T is the amount in an account growing at an interest rate of R per year, and we are depositing / withdrawing H dollars per year, then if P is compounded continuously, it turns out that P prime will be modeled by RP plus H. And this you can figure out by actually using the compound interest formula and taking the limit of that formula as time goes to infinity, as n goes to infinity, where n is the number of times compounded per year. So that's another thing. So another question that I could ask is something like, okay, there's money into an account. It's growing at, say, 5% interest compounded continuously. If I start out with $1,000, how much money will I have after 10 years, right? So something like that you can ask. And you would solve this using a separable differential equation. It'll be very similar to the calculation that we're doing here, so I'm not going to do it again, but now you kind of know. So that's another scenario where this will work out, and that's all I wanted to do for this lesson. Okay. Now, the main thing I want to do today is I want to talk about first order linear ODEs. Okay, so remember yesterday we looked at what linear meant. And so now I want to talk about first order linear. Now, based on the definition of linear, here's what first order linear means. It means you're looking at a differential equation that has this form right here, right? So dy dx plus some function of x times y equals some other function of x. If you have a first order differential equation and you can write it in that form, this is called a first order linear differential equation. So that is here is what makes a first order linear differential equation. This, by the way, is called the standard form of a first order linear differential equation. This is standard form. Now, standard form is something that's used in general. This is when you take the highest derivative and you write the equation in such a way that its coefficient is 1. And a lot of times, theoretically, what we do is we start off with the equation in this form because it's a lot nicer to apply methods that we'd want to apply. So this is called the standard form. Okay. So that's something that you should know, what a first order linear ODE is. Okay, because they have a method that go with this kind of differential equation. And remember, yesterday I was telling you guys, the important thing when talking about differential equation is you want to know the form and you want to know the method that goes with the form. Yesterday, we looked at the form of a separable ODE. That means you can write it as f of y dy equals g of x dx. Okay, this is another form of an ODE. This is a first order linear. This means the form is dy dx plus p of x times y equals g of x. Now, in the event that your g is 0, this is a separable equation. You can just add the p of y to both sides and then divide by y and multiply by dx, and you can separate it. If the g is non-zero, then it turns out that this is not separable. Okay, how do we deal with this kind of differential equation, which also shows up often enough? You can also notice that the population model I just spoke about, you can actually think about it in this form, but because your g was a constant, we were able to separate the variables. We can't always do that. And because the p of x was a constant also. But in general, this is not going to be separable if your g of x is not 0 and your p of x is a variable function. Okay. So here's an example of a first order linear differential equation. Ln of x times y prime equals that. Now, first thing I want you to realize is that, so we know this is first order linear, since if I had the ln of x, y prime, plus x to the minus 1y equals e of x, I can divide both sides, divide all sides by ln. As long as it's not 0. And you'll notice that this has the form y prime plus p of x y equals g of x, right? Because the p, the guy that represents the p would be here. That's my p. And the guy that represents the g would be here. That's g. Okay? So sometimes it's going to take a little bit of algebra for us to realize what kind of equation we're looking for. So this is why your algebra skills are going to be important. You need to be able to look at something and understand, oh, I can algebraically manipulate this to look like this form. Okay? So this here is an example of a first order linear ODE. You'll also notice that this is not separable. You cannot, using multiplication and division, separate the x's and y's. Okay, you can't write this in the form f of y dy equals g of x dx, right? You're not going to be able to get into that form. Okay, so I know that this is a first order linear, it is not separable. So the technique that I showed you yesterday would not work for this guy. So what would work for this guy? Okay, so let me show you how to deal with these guys. So here I have ln of x, y prime, plus x to the minus 1 y equals e to the x. Here's something you can notice. See the left side? The left side is actually ln of x times y all prime. Do you see that? Because this would be by the product rule. This would be you leave the ln, differentiate the y, plus you leave the y and you differentiate the ln. Do you guys see that? So it turns out here's a first order linear differential equation, but the left side has a very nice pattern to it. Now what I can do is I can integrate both sides. By the fundamental theorem of calculus, the integral kills the derivative. And then I can actually solve for y by dividing both sides by ln. All right, nice. So we understand what happened here? Okay, cool. Let's do another example. Okay, here's another one. First order linear. What do we do? How do we solve it? Ideas, what do you see? Okay. And what would that allow us to do? So if I divide by e to the minus 2, then factor it. So we have dy dt minus this would be e to the 2t times e to the minus 2t y equals e to the 2t times t squared. And how would you separate the variables here? So first of all, yes, this is first order linear. Is it separable? It's not separable. So separation of variables isn't going to work, but it seems here like Eugene sees it. It's the same thing as the last example. Notice that the left side is what I would get if I took e to the minus 2t times y and differentiated it. Right? By the product rule, I would get the left side of the original. Now what I can do is I can integrate both sides. And then I can multiply both sides by e to the 2t. And that's the answer. Are we good? We got it? Okay. Any issues, concerns with what just happened? Right. So Kevin is suspicious like me. Like if I was in a class and I had someone showed me this, yeah, but is that always going to work? Like, is the left side always that nice? Like, what if this wasn't an e to the 2t in the front? What if it was e to the minus 3t, but everything else was the same? You do realize that this method that I just did now would not work. Right? So that's the obvious question. Does the left side always look like this? Will this always work? Because it seems very convenient, suspiciously convenient, right? Yeah, Jhevon showed me these two examples. Oh, hey, the left side was actually the product rule. If I just reverse the product rule, this thing works out. That was very nice, very convenient. Of course, all first order linear differential equations in real life are going to conform to the product rule. No, it turns out the definition, that is not a requirement. There is no requirement that the first order linear differential equation has to somehow conform itself to the product rule. Okay, so that is an obvious question, right? These two examples, they were too nice. Okay, so now that leads to the question here that I was hoping someone would ask. Does a method like this always work, right? Actually, the answer is no. And yeah, so I guess we're done here. Thanks for stopping by. Okay, I'm kidding, right? So it turns out that there are situations where this will not be the case, that the left side is not going to be this nice form. However, it turns out for a first order linear differential equation, theoretically, we can always transform it to look like a form like this, right? This leads to something that we call the method of integrating factors. Okay, so when it comes to first order linear differential equations, especially the scenario in which it's not separable, okay? So this method will work even if it is separable, but it's harder to get it to work if it's separable, so you just do it the separable way. This is called the method of integrating factors, okay? So what an integrating factor is the following. You have a differential equation, okay, first order or otherwise. Integrating factor is a general term. You have a differential equation. If you can find a function where if you multiply the differential equation, it modifies it in such a way that it becomes convenient in some way, then that allows you to integrate something very nicely, because to solve a differential equation, you're going to have to use integration. That function is then called an integrating factor. It turns out if you have a first order linear differential equation, you will always have an integrating factor. There will always be a function out there that we can find that if you multiply the differential equation by, it will transform the left side into the product rule, right? Which is kind of crazy that that would even work, but it can actually work. And let me show you. So normally we call this, yes, you will always be able to do this. I know it's very strange. This is going to be something that's going to be a reoccurring theme in this class. There are going to be amazingly convenient things that can work out sometimes. And then there are going to be times when we're going to just kind of have a hopeful guess that something's going to work out and is going to work out. We're going to get to that. But in this case, in a first order linear differential equations, yes, you will always be able to manipulate the equation in such a way that you end up in an easy case like the first two examples here, even if in the beginning it is not that situation. So here's how we do it. So we have y prime plus p of y equals g. So suppose mu of x is an integrating factor. What must it behave like? How can I know that I can find such a function? Well, if I have this guy, this is not, I don't know why it's doing that. Okay, it's probably doing that because of this. If I have this, I don't know why it's not allowing me to highlight it. Okay. Copy. Okay, so let's say I have this equation and I multiply through by some function mu, right? Now I don't know right now what this function is. However, I know what I want. We want mu y prime plus mu times py to behave like the product rule. What does this mean? So let's see who's paying attention here. Like if I want the left side to behave like the product rule, give me a requirement. What would need to happen to the left side in order for me to be able to think of it as a product rule? Can you think of a requirement? Almost. You're almost there. You're a little bit off. What do you mean? What is parentheses of u? U prime. Notice that mu times p must be equal to mu prime, right? Because then what would happen is you would have mu times y prime plus mu prime times y on the left. So if I can find a function such that mu times p is equal to mu prime, then that will actually work out. I will be in the situation that I was in the first two examples. So now we have to worry about this. But what is this here? Who can tell me what that is? If you were to call that equation by a name, define it as some special kind of equation, what would you say it is? It is an ODE. It is a first order ODE. Get more refined. It is a separable ODE. So yeah, we're going to be like Thanos here, and we're going to use an ODE to destroy the ODE, right? So if I can get this ODE to work out, I will be able to get the original ODE to work out. And this ODE happens to be separable. In fact, I can say here, this means that d mu dt is equal to mu times p. I can write this as d mu over mu is equal to p of t dt. I can integrate both sides. The left side is going to be ln of mu, absolute values. The right side is going to be the integral of p of t dt. Now we don't know what the p is, so I can't really tell you a formula for it, but whatever its integral is, that's what it's going to be. And at this point, I can solve for mu. This means that my mu is going to be e to the integral of the p. And so this leads us to a summary. Given y prime plus p of t y equals g of t, this is a first order linear ODE. Its integrating factor is mu equals e to the integral of the p. Yes, p of t. Remember, p is a function, right? If you go back to the definition, p is a function. So P is not like a constant or anything. It's a function of the independent variable. So I wanted to emphasize that because I didn't want students to make the error of thinking, oh, this is just going to be PT plus C because P is a constant. It's not a constant. It can be it's some arbitrary function. It is whatever the coefficient of Y is when you're in standard form. Oh, I already started doing that down here. Right, so this leads to the integrating factor method. Let me get rid of this. Okay, and this is again, in theory, this works out if you can actually find the integral of the P, which in a math class, it's always going to be a function that you can integrate. However, in the real world, you might have to use a computer algebra system to help you integrate it, or use some numerical approximation method. However, in theory, if we can find this integral, I can actually solve this ODE. So given a differential equation in this form, we can solve the ODE by doing the following. 1, find mu equals e to the integral of the P. 2, multiply through by mu. So you would get mu times y prime plus p mu y equals mu times g. 3, the left side is the product rule. The left side will become mu times y all prime. We literally solved for that to happen. We forced this to happen. And so what can happen now is 4, integrate both sides. And solve for y. So then you would get mu times y is equal to the integral of mu g plus a constant. And then you would end up with your y is the integral of mu g divided by mu plus a constant. And that's what your solution is going to look like. This here is called the method of integrating factors. So it turns out, even if you have a first order linear differential equation where the left side does not behave in a nice way, you can still force it to behave in the nice way. So, for example, and I want you to be aware of, it has to be in this form. It has to be in standard form for you to even start this method. Note, maybe I should put this in red. Note, we must start off from standard form, because your P of t is going to be the coefficient of y when you're in standard form. Now, assuming I put it in standard form, P is the coefficient of y. All I need to do is find e to the integral of P. I'm going to multiply through by that function. It will transform the left side into the product rule, and this allows me to solve the ODE. Let's do some examples. We have a bunch of examples to do here. Did I miss anything else? Yeah, this is all we have for this section. So I'm going to do the first example, and you guys are going to help me with the others. Okay, so I want you guys to see this in action, and then you guys are going to do this. You guys are going to help me do the rest of them. Okay, so here is an example of a first order linear ODE. In fact, this one is in standard form, right? It is y prime plus p of t times y equals e to the minus 3t. In fact, here my p of t is the function 2, and my g of t is going to be the function e to the minus 3t. Notice here that the left side is not in product rule form, okay? However, what I can do here is create such a situation. Mu is going to be e to the integral of 2 dt. This is going to be e to the 2t. Now, we don't need the plus c. It's not that it would be wrong to put a plus c, but it's unnecessary. It's going to work with or without the plus c, so it's just nicer to leave it off. Okay, so any integral of p of t is going to work. So I'm going to choose the easiest one. Choose the one where the plus c is 0. What this means is I'm going to multiply through by e to the 2t. And it turns out that the left side will become the product rule. It's always going to be the mu times the y all prime. Right? You can check this with the product rule. This will happen once you multiply through by the integrating factor. Now, because we know this is always going to happen, you can skip this step. And just go to the form mu times y all prime equals g times mu, right? Because that's always going to happen. We know that's going to happen. So this line right that I wrote, this line right here is inevitable. It's always going to happen. Okay. Now, what do? Well, we can integrate both sides. Integrate, integrate. So the left side, when I integrate it, fundamental theorem of calculus just says the derivative dies. On this side, the integral becomes e to the minus t plus c. And then I can divide both sides by e to the 2t. And that is the solution to this differential equation. This is a function who, if I take, it will satisfy this differential equation, and it does not have any derivatives in it. This is the solution to the ODE. So yes. So the method of integrating factors is the method that I outlined here. It's always going to be these 4 steps. And again, just to re-emphasize what I mentioned yesterday, the method is very dependent on the form of the differential equation that you have. These are the 4 steps that you apply if you have a first order linear differential equation that is not separable. This method does not work for general first order equations. So that I need to be clear. This is the integrating factor method. And you'll notice here I put in parentheses for first order linear ODEs. It works both in the separable and non-separable case, but it's overkill for the separable case. So for the separable case, just separate it and just find the solution that way. For the non-separable case, it's very important. So yeah, it's always going to be these steps. So if I, like on a test or a quiz, what's going to happen? Yeah, it is very sweet. what you have to do is you have to classify the ODEs, right? So if I give you a bunch of first order differential equations, you need to be able to look at them and know, oh, this one is linear, this one is not, this one is linear, this one is not, right? This one is separable, it's not separable, etc. But once you come up with a classification and you know what I am looking at is a first order linear non-separable ODE, then this method is going to work. Right? If you have a separable ODE, the method we discussed yesterday is going to work. And so this is what I meant by yesterday. This class is going to feel a lot like Calc 2. It's just a situation of, it's a situation where I need to know what situation I'm in so I know what method will work. So just like in Calc 2, when you're like, oh, for this kind of integral, substitution will work. Oh, for this kind of integral, integration by parts will work. For this kind of integral, a trig substitution will work. You need to know how to look at an equation, identify what kind of scenario you're in, identify what method would work for that scenario, and then apply the scenario, apply the method. This is the method for first order linear non-separable ODEs. All right, now hopefully we have that cleared up. Let's finish these guys. All right, so someone chime in here and tell me how to do this. Okay, so here's an example. And of course, another thing I mentioned yesterday, really engage in active learning. It's more important now than ever, now that we're in this distance learning thing. You really want to not wait for me to write down the solution or not wait for one of your classmates to tell you what to do. Actually try to do something, try something, and then make a suggestion. Right now, like in a few seconds. What's the first thing you would do here? Find mu. Right, and mu is mu. It's a Greek letter. And I, for one, it's funny, I, for one, am, it's very funny that I'm making this correction. There was a point when I was teaching this class where I was going through a method and there were Greek letters all over the place. And there was, and in the method, there was the Greek letter xi, but I kept calling it psi. And there was a Greek person in the class and it was like, they said, you kept calling that letter by the wrong name. It was driving me crazy. It's like the letter is F and you kept calling it W, like the whole time. It was driving me crazy. So yes, I apologize to all the Greek people. Yeah, 20 years down the road, there's gonna be like something, it's gonna surface. Here's an old video of Jhevon just offending the Greek people. Yeah, then I'm gonna have to send out a tweet apologizing. I apologize if I offended. Yeah, okay. All right. So yeah, it's very strange that I'm correcting people on Greek letters, but yeah, it's actually MU is the English way to spell that. But yeah. So, all right, let's, all right, so, all right, Eugene is like, mu is e to the integral of, right. So here, you realize that this is a first order linear ODE. You can also realize this one is actually separable. By the way, this is separable. Okay, so you could have done it the separable way, but how do I know it's separable? Y prime, I just noticed it was separable. You can write it like that. Then what you can do is you can like factor out an x. Then you can write it as dy over 2y plus 1 equals x dx. Then you can integrate both sides. So that would give you 1/2 ln of 2y plus 1 equals x squared over 2 plus c. This will give you that ln of 2y plus 1 is equal to x squared plus c. This would mean that 2y plus 1 would be ce to the x squared. And so your y is going to be ce to the x squared minus 1/2. Okay. So this was separable, just went off on a tangent there. But let's do the integrating factor method. Let's do the int factor method and compare. Okay, so for the integrating factor method, let me copy this guy. Now, of course, you'd find the c here. Where did the 2 go under x squared? Oh, here I multiplied both sides by 2 because I wanted to solve for y. So I took this equation and I multiplied both sides by a half. Multiply both sides by 2. So that kills the half here. And that kills the half here, that kills the half here. And I have this. Okay, so this was a situation where it is separable. And so, you know, I typed this out, I didn't notice, but now when I'm noticing, I'm focusing on solving it, I'm like, oh, that's separable, right? So you should be able to recognize something as separable versus not. So this is actually separable, you could do it a separable way. However, let's do the integrating factor way so we can actually compare. And it's just a happy accident. Now you can see that it'll work even in the separable case. So your mu would be e to the integral of minus 2x dx. This is, of course, going to be e to the minus x squared. This means that the differential equation can be written as e to the minus x squared times y all prime. And it would be the same as x times e to the minus x squared. Then I can integrate both sides. This side becomes e to the minus x squared y. This side is going to become minus 1/2 e to the minus x squared plus a constant, right? And I didn't write it because, you know, we learned this like a year and a half ago in Calc 2. I did a substitution. Just did it in my head. Anyway, now we can multiply both sides by e to the x squared. So this gives us minus 1/2 plus c times e to the x squared. And if you look at our last one, hey, it's the same. So I got the same answer. Now we know that y of 0 equals 0. So this means that 0 is going to be minus 1/2 plus c e to the 0. So this gives us that c is 1/2. And so finally our solution is 1/2 e to the x squared minus 1/2. And that is our particular solution. So this particular example, you had a couple methods that can work. You can notice it was separable and you would have gotten the answer that way. Or you can notice that it's a first order linear. Just hit it with the integrating factor method. The integrating factor method is going to work whether or not it is separable. Hopefully we got it. Let's make sure we got it by having you guys go through another example. How about this one? Now this one is not separable. So in case you were thinking that, oh, maybe it's Jhevon's trying to trick me again, give me another separable. This one is not separable. Okay, so we have divide through by t, yes? So this gives us y prime plus 2 over ty equals sine t over t. Why? Because this puts it in standard form. Remember, our method needs to start off with standard form. Very common error is for students to forget to do that, and then they're going to identify their p, in this case, as the number 2. That would be incorrect. Your p is actually 2 over t. So now what? Now that it's standard form, what's the next thing we do? Find mu. Mu is going to be e to the integral of the p, which we now know is 2 over t. This is going to be e to the 2 ln t. This is going to be e to the ln of absolute value t squared, which is just t squared. So the left side is going to become t squared times y all prime, and the other side is going to become t squared times sine t over t, which is going to become t sine t. Now what I can do is I can integrate both sides. The left side is going to become t squared times y. The right side is going to become the integral of t sine t. How do I integrate t sine t? Right, integration by parts. Integration by parts means you have to identify a u and a dv. The u is chosen by Lyautey. In this case, that's going to be the t. The dv is chosen by Lyautey. In this case, that's going to be the sine of t. So it's going to be u times v minus the integral of v du. So it's going to be one function times the integral of the other minus the integral of the same function times the integral of the derivative of the first function times the integral of the other. So this is going to be minus t cosine t plus sine t plus c. That is a good question. Am I breaking up to anybody? Okay, so Insha, it's on your end. Okay. So here what I did was integration by parts, int by parts. So this is going to be u times v minus the integral of v du. Okay, so that's going to be the integral. And then this means that my y is what I would get if I just divide both sides by t squared. So this is minus cosine t over t plus sine of t over t squared plus c over t squared. Students often forget the c, so they'll miss that whole c over t squared function. That is going to be our solution here. Yes. Okay, so we were given an initial condition. Yeah, thanks for reminding me. I forgot that for this one we had an initial condition. So once you're given an initial condition, yes, you have to find the c. So we were given that y. So we were given that y of pi over 2 is 1. So yeah, we need to deal with that. Now, since y of pi over 2 equals 1, this means that I plug in y equals 1 when I plug in t equals pi over 2. Okay, what's cosine of pi over 2? 0. What's sine of pi over 2? 1. Right. So this now becomes, well, this is going to be 4 over pi squared plus 4 over pi squared times c, which means I can take 1 minus 4 over pi squared, then multiply by pi squared over 4, and that will be c. And so my c is going to be pi squared over 4 minus 1. And so now I can go back. So our original thingy here, that was our original solution. That's the general solution. So at this point, I need to plug in that, that c. Okay. Are we clear on what happened? Okay, great. All right, someone tell me how to do with this last one right here. Okay, so we don't need to find the c in this case. We weren't given an initial condition, so we just want the general solution here. Right, multiply by x to put it in standard form. I believe for this one, you're going to notice something that happens. Okay, so this would be dy dx minus 2 over x, y equals x squared cosine x. Then, what do we do? Next step? Next step is to find mu. Mu is going to be e to the integral of the p, which is the coefficient of the y when put in standard form. This is going to be e to the minus 2 ln x. This is going to be e to the ln of absolute value of x raised to the minus 2. Now that's going to be the same as positive x raised to the minus 2. So now I'm going to multiply both sides by that. So this is going to be x to the minus 2 times y all prime. The right side is going to be, well, it's just going to become cosine of x. Then I'm going to integrate both sides. This side become x to the minus 2y. That side is going to be the integral of cosine, which is positive sine x plus c. And so our y is going to be x squared sine x plus cx squared. And that is our solution, general solution. Okay, so today we learned about population models, the naive model called the harvesting model. We also learned about first order linear ODEs and the integrating factor method for solving them. So yeah, went through a bunch of examples. For tomorrow, we're going to start to do examples. The next thing we want to cover is homogeneous first order, which is what we have here. Also, maybe we might be able to get into the next topic. I'm not sure. Mu equals e to the, yes, it's right here. Okay, Incha is back. Yes, today is Thursday. So our next class is Tuesday. So here, yeah, I was being a little sloppy here. There is technically a dx here, but yeah. Okay, so our next class is Tuesday. Now, next Tuesday, we're going to start off with a quiz that covers everything that we did this week. And I will let you guys know over the weekend what platform that's going to be on. By this weekend, I'm definitely going to decide on a platform and how that's going to be operated. One thing I do need to make sure that you guys check out, if any of you have accommodations, you need to make sure that the Disability Services Office reaches out to me so that I can make sure that you will get the extra time that you are accommodated. Yeah, I'll probably start the class with that quiz, which also reminds me, class starts at 1:20, okay? So make sure you're here at 1:20. So I know when I sent out the Zoom invite, it says 1:30, but that's because I couldn't actually select the time 1:30 on the invite. The time blocks that it goes by every half hour. So it says 1:30 on the Zoom, but our official start time is actually 1:20. So the quiz is going to be from like 1:20 to 1:30. The first, yes, next Tuesday. Maybe I should write that down. First 10 minutes of next class is a quiz. Class starts at 1:20 p.m. Covers. So the quizzes are not, it's not going to be on Blackboard, but I'll let you know over this weekend. Probably not on Blackboard. It covers everything done this week. So it means up to first order linear. All right. You should, I mean, if you can't access the homework, if you emailed me and you contacted the administrator, which is a guy by the name of Paulilo, it shouldn't take too long for that to be corrected. So then I believe the first homework date, quote unquote, is on the 7th, which is Sunday, I believe. But that's just an orientation. The first official homework is due like the 20th. Yeah, it's the same guy. So remember, make sure that you reset your CCNY email password. Someone posted the link in the comment section, just in the chat box just now. reset your password and try to log in with the new password. And if that does not work, then you reach out to me. I'll check that you're in the WebWork roster. If you're in the WebWork roster and you reset your password and you still can't get in, then that's when you reach out to Paulino. Okay, we're going to wrap up there, guys. Hopefully you understood everything that's in this class. Starting next class, the integrations that we're going to need to be doing are going to start getting more sophisticated. So definitely review things like integration by partial fractions, integration by parts, all that good stuff next week, because the integrations, we're starting off really slow, really easy, but eventually the algebra and the calculus is going to go to a higher level than we've been doing. So review your calculus, review integration, review differentiation, just all the computational stuff. That's going to be very important moving forward. But yeah, we will wrap up there for now. Make sure that you check that you get into your homework. Make sure that you received an email from me today from Jupiter Grades, and we will stop there. So that is it. All right. Thank you all for showing up. I will see you guys. Yes?
Yeah, I did not get an email from the Jupiter Grades.
Okay, so make sure you email me telling me that, and I'll make sure to double check.
Should I email you like in the
email me right now. Right now.
In the CCNY email?
No, the Gmail.
Okay, got it.
Oh, the email on the syllabus.
Sure, thanks.
Okay, all right. Take care, guys. That's it for today.